Welcome back to Introduction to Higher Mathematics. In our last lecture, we rounded out our repertoire of proof techniques using quantifiers. We saw that to prove a statement of the form for all x, p of x, we must let x be arbitrary, and show that p of x is true no matter what. On the other hand, to prove a statement of the form there exists an x such that p of x, all we need to do is find an x that makes p of x true, although this is sometimes easier said than done. We also saw that to prove uniqueness, you can assume p of x is true for two different values, and then show they must be the same value after all. We met the well-ordering principle of the natural numbers, the fact that every non-empty subset of n has a smallest element. Based on this fact, we learned a new proof method called proof by mathematical induction, in which we must first prove that p of 1 is true, and then prove that if p of x is true, then p of x plus 1 is true. We also introduced strong induction, which for the induction step assumes that p of 1 through p of x is true, and then shows that p of x plus 1 is true. Finally, we discussed the important difference between deductive and inductive reasoning, and why inductive reasoning isn't valid as a method of proof. But remember, mathematical induction is actually a kind of deductive reasoning. Now it's time to start building some relationships between sets. Let's start with a new definition. A tuple is an ordered list of elements, usually put between parentheses instead of curly braces. A tuple with n elements is generally called an n-tuple. A one-tuple is called a singleton, and you're probably already familiar with two tuples and three tuples from graphing in 2 and 3 dimensions, where you probably called them ordered pairs and ordered triples, respectively. If you're wondering why we're using such a strange name for these new objects, it's because tuple is a generalization of the words single, double, triple, quadruple, quintuple, sextuple, and so on. There are a couple things that set tuples apart from sets. First of all, unlike a set, a tuple always has a first element, a second element, and so on, depending on the size of the tuple. So the ordered pair 1, 2 is not the same as the ordered pair 2, 1. Second of all, tuples can have repeated elements. So for example, 1, 1 is a valid tuple. Tuples lead us to a new way to combine two sets together, called the Cartesian Product, named for French mathematician and philosopher René Descartes. A popular legend has it that Descartes, who studied at the Jesuit College of La Flèche, was lying in bed one morning. He was a very sickly child, so his teachers let him stay late in bed. Even so, he managed to keep up with his studies. Anyway, as the legend goes, this one particular morning, Descartes saw a fly crawling across his ceiling. Staring at the fly for a long time, he wondered if he could come up with a mathematical way to trace the fly's path across the ceiling. After pondering for a while, he decided he could describe the fly's position at any point in time as an ordered pair of numbers. The first one telling how far along one of the walls it was, and the second one telling how far away from the wall it was. Thus the Cartesian coordinate system was born. Descartes in that moment had stumbled upon what would be the basis of his book, La Géométrie, in which he laid the foundations for analytic geometry, also known as coordinate geometry, which for the first time in history united algebra and geometry, long thought to be two completely different fields of mathematics, into one single subject. Interestingly enough, Descartes wasn't the one who invented the coordinate axes. Those were developed later by the commentators of his book. Whether or not the story of the fly on the ceiling is true, the point remains that Descartes had found something remarkable that would forever change mathematics. With this in mind, let's talk about what the Cartesian product is. Suppose we have two sets, A and B. The Cartesian product of A and B, written as A times B, is the set of all possible ordered pairs, for which the first element is from A and the second element is from B. So for example, suppose A is the set 1, 2, 3, and B is the set x, y, z. Then the Cartesian product A times B would have 9 different ordered pairs in it. 1x, 1y, 1z, 2x, 2y, 2z, 3x, 3y, and 3z. Or, for another example with which you may be even more familiar, a standard deck of playing cards has 13 ranks, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king, and 4 suits, spades, hearts, clubs, and diamonds. Suppose we let R be the set of all ranks, and S be the set of all suits. Then the Cartesian product R times S will represent the entire deck of 52 cards, accounting for every possible combination of rank and suit. An important thing to note is that the two sets in a Cartesian product don't necessarily have to be different sets. Given a set A, there's nothing stopping us from finding the Cartesian product A times A. In this case, we have what's called a Cartesian square, and it's often simply written as A squared. The familiar Euclidean coordinate plane from analytic geometry is a great example of this. Since both the x and y coordinates are real numbers, the set of all points in the real plane can be represented as r times r, which is often shortened to r squared. Alternatively, we can represent a point lattice, which is the set of all ordered pairs of integers, such as on a geoboard, as z times z, or z squared. We can further generalize the idea of a Cartesian product by multiplying more than two sets together. Suppose C is the set red, green, blue. Then we could take A times B and find its product with C. We would get a set of 27 elements. Each element would be an ordered pair, for which the first element is itself an ordered pair of elements from A and B, and the second element is from C. But now think about what would happen if we first found B times C, which would also have 9 elements, and then found the product of A and our new B times C. We'd still have a set of 27 ordered pairs. But this time the first element would be from A, and the second element would be an ordered pair of elements from B and C. These sets in the strictest sense are different. But look carefully. If we were to somehow ignore any inside parentheses, and instead only concentrate on the elements of A, B, and C in the order they were listed, both of these sets would yield the same set of ordered triples. So if this set of ordered triples is what we in fact want, we write A times B times C without any parentheses. This is called a ternary Cartesian product. Let me explain what that means. Recall that in Lecture 5 on sets, we talked about what an operator is, and we discussed the common operators used in set theory and in logic. In math and computer science, the arity of an operator tells us how many arguments that operator accepts. In other words, how many things it works with. The classic operators you first learn in elementary school, addition, subtraction, multiplication, and division, are known as binary operators. That is, operators with an arity of 2. Because whenever you use one of those operators, you need 2 numbers, one on the left and one on the right. On the other hand, the negative sign you learned thereafter is what's called a unary operator, with an arity of 1, because the negative sign acts on only one number, or perhaps an entire expression, rather than being used to connect two expressions together. See if you can figure out which of the various connectives and operators you've learned for logic and set theory are unary, and which are binary. Anyway, an operator with an arity of 3 is called ternary, an arity of 4 is called quaternary, an arity of 5 is called quinary, and so on, with an arity of n simply being called n-ary. It's not so much important that you know the names of these different arities, but rather that you understand the concept here of extending an operator to any number of inputs. So as opposed to the binary Cartesian product, the n-ary Cartesian product, written with no parentheses, gives the set of all possible n-tuples made by combining n different sets. Again, as with Cartesian squares, we can find the n-ary product of a set, A, with itself, which will be called a Cartesian power. So Euclidean space, which can be thought of as the set of all ordered triples of real numbers, can be written as r cubed. Now that we've seen Cartesian products, it's time to talk about relations. Suppose I have a few kids, perhaps we'll call them Yakko, Wacko, and Dot, and some food, perhaps hamburgers, hot dogs, and pizza. We might ask, what foods do Yakko, Wacko, and Dot like? Let's say that Yakko likes hamburgers and pizza, Wacko likes all 3 because he loves to eat, and Dot likes none of the three, preferring a salad instead. So, how can we represent all this information mathematically? Well, if A is the set Yakko, Wacko, Dot, and B is the set hamburgers, hot dogs, pizza, then first of all, consider the Cartesian product A times B, giving all possible ordered pairs of kids and food. Then, who likes what food could be represented by using these ordered pairs. For example, the fact that Yakko likes hamburgers could be represented by the ordered pair Yakko hamburgers. Now, suppose we were to take all pairs that corresponded with who we said likes what food and put them in another set. We could call it L. Then L is a subset of A times B. We call this subset a relation between A and B. So, if we say that Wacko pizza is an element of L, it means that the two elements are related in the way we specified. Wacko likes pizza. You can think of L as the truth set of a predicate, perhaps little l, of x, y, that evaluates to true if x likes y. There's also a shorthand we can use if the ordered pair xy is an element of L. Often we can just write xly, which reminds us that it means that x likes y. The first set is called the domain of the relation, and the second set is called the codomain. So in our example, the domain is the set of kids, well, characters really, and the codomain is the set of foods. A common and quite intuitive way to visualize relations is to use what's called a graph. This isn't a graph like what you learned about in coordinate geometry, to graph lines and parabolas and stuff like that, but a somewhat more basic concept. A graph is a collection of points, usually called vertices, and lines, referred to as edges. So this graph has 4 vertices and 7 edges. Graphs were first studied by Leonhard Euler in 1735 because of a very interesting problem. There was a city called Königsberg in Prussia, through which ran the Pregel River. The city included 2 large islands in the middle of that river. Connecting the various parts of the city were 7 bridges. The people of Königsberg would sometimes try to find a way to walk through the city, crossing each bridge exactly once. The starting points and ending points didn't necessarily have to be the same. But nobody could figure out a way to do it. They always ended up having to cross some bridge more than once. Euler, being the talented mathematician he was, set out to study the problem by reducing it to a graph, much in the same way that the 4-color problem was reduced to a graph as you saw in the first lecture. After pondering over the graph representation of the city and its bridges, Euler concluded that it was in fact impossible to traverse the city while crossing each bridge exactly once. I won't go into the actual solution here, but feel free to look it up if it interests you. Euler's study of the 7 bridges of Königsberg and the paper he released in 1736 regarding his solution were the birth of what we now know as graph theory, a very powerful subject with endless applications. Relations can be drawn using a specific kind of graph called a directed graph or digraph. When we draw a digraph to represent a relation, we put all of our elements of the domain on the left and all of our elements of the codomain on the right. Often we'll put an enclosure around the domain and codomain as well, just to make things clear. Then, if an ordered pair xy is in the relation, that is, if x is related to y, we draw an arrow, starting on the left and ending on the right. The direction of the arrow very much matters, which is why we call it a directed graph. So this is what the graph would look like. Yakko likes hamburgers and pizza, Wacko likes hamburgers, hot dogs, and pizza, and Dot likes none of the 3. Now, when we study relations, many times we're interested in relations in which the domain and codomain are actually the same set. If we have a relation between a set A and itself, usually we simply say that it's a relation on A. A relation on A will be a subset of A squared. For example, let's make A a different set of 3 people, say Archie, Betty, and Veronica. Now, we'll use the same relation we used before, x likes y. Suppose we have the following relation. Archie likes both Betty and Veronica. Betty likes Archie, but does not like Veronica, at least not when she's fighting Veronica for Archie's affection. Similarly, Veronica likes Archie, but does not like Betty. Also, since Veronica is somewhat of a narcissist, we'll say that Veronica likes herself as well. So our relation can be drawn with 5 arrows, like this. There are 2 important kinds of relations on a single set that we're going to take a look at: equivalence relations and order relations. Equivalence relations show that 2 elements from a set are considered equal in some way. So the classic example, unsurprisingly, is good old-fashioned equality. We can use equality to look at what exactly defines an equivalence relationship. For something to qualify as an equivalence relation, it has to have 3 specific properties. First, an equivalence relation must be reflexive. This means that every element in our set must be equivalent to itself, or symbolically, if our relation is called R, then for all x in A, the ordered pair XX must be in our relation R. So for example, the number 5 is in fact equal to itself. This may seem almost trivial, but there are plenty of relations that don't have this property. For example, consider the greater than relation. 5 is certainly not greater than itself, is it? In fact, the greater than relation is actually called irreflexive, because no number is ever greater than itself. Second, an equivalence relation must be symmetric. This means that if x is equivalent to y, then y is equivalent to x. Or symbolically, for all x and y in A, if the ordered pair xy is in R, then yx must also be in R. So for example, if 1/2 is equal to 2/4, then 2/4 is equal to 1/2. Again, the greater than relation is an example of something that does not follow this rule. If x is greater than y, then y is definitely not greater than x. Finally, an equivalence relation must be transitive. This means that if x is equivalent to y, and y is equivalent to z, then x is equivalent to z. Symbolically, we'd write that for all x, y, and z in A, if the ordered pairs xy and yz are in R, then so is the ordered pair xz. For a non-example of the transitive relation, consider our Archie love triangle. Betty likes Archie. Archie likes Veronica. But at least a good amount of the time, Betty does not like Veronica. So our like relationship is definitely not transitive. As a side note, the understanding of equality as an equivalence relation is something we often take for granted without realizing just how important it is. Research in 2010 showed that about 70% of middle grade students in the United States exhibit misconceptions about the real meaning of the equal sign, while nearly none of the international students in Korea and China had any of these misconceptions. This is probably because in many cases in the United States, children who are first being taught the basics of math don't think of the equal symbol as something that shows a relationship, but rather an operator that means put the answer on the right side of these 2 little lines. So many students, given true or false questions such as 5 equals 5 and 4 equals 1 plus 3, would actually answer false. Remember, just because something seems obvious to you doesn't mean it's obvious to everybody else. Always keep that in mind to make your explanations and your proofs as lucid as possible. There are lots of equivalence relations that we use in mathematics. Equality is just the one you're no doubt familiar with by now. But there are lots of others. In geometry, for example, congruence of geometric figures is an example of an equivalence relation. So is similarity of figures. In logic, logical equivalence of 2 propositional expression is in fact an equivalence relation, as of course we'd expect by the name. We can even find equivalence relations in everyday life, such as has the same birthday as. By the way, when we define an equivalence relation on a set, in the process we end up splitting or partitioning the set into what are called equivalence classes, sets of all elements that are equivalent to each other. Suppose little a is an element of set A. Then the equivalence class of little a is just the set of all elements of A that are equivalent to little a. So, for example, if our set is the set of people living and dead, and our equivalence relation is has the same birthday as, then since I was born on March 26th, my equivalence class is the set of all people who were born also on March 26th. What's more, equivalence classes are always disjoint, meaning they have no elements in common. It would make no sense to say that my birthday is both March 26th and March 27th. I'd get double the presents, and everybody else would be jealous. See if you can prove this, by the way. It's a good exercise in proving uniqueness. The other kind of relation that shows up a lot in mathematics is order relations. Rather than splitting a set into equivalence classes, order relations establish sort of a hierarchy in our set that let us compare different elements. The basic kind of order relation is called a partial order. Like an equivalence relation, a partial order must be both reflexive and transitive. But where the two differ is the symmetric property. Rather than being symmetric, a partial order must be anti-symmetric. This means that if x and y are different elements of A, and x is related to y by our partial order, then y must not be related to x. For example, we'll define the power set of a set as the set, or more correctly the family, of all possible subsets of that set. For example, suppose A is the set 1, 2, 3. Then the power set of A, written P of A, will contain 8 elements, each of which is one of the possible subsets. We have the null set, the set containing 1, the set containing 2, the set containing 3, the set containing 1 and 2, 1 and 3, 2 and 3, and finally the whole set itself, 1, 2, and 3. Then the subset relation on this power set is an example of a partial order. For example, the set 1, 2 is a subset of the set 1, 2, 3. But 1, 2, 3 is not a subset of 1, 2. But remember, 1, 2, 3 is a subset of itself, so the reflexive condition is satisfied. When we can establish a partial order on a set, we call it a partially ordered set, or a poset for short. So the power set of 1, 2, 3 with the subset relation is a poset. Something important to note, however, is that a partial order does not necessarily let us compare any two elements of a set. Note that the set 1, 2 is not a subset of the set 3, but neither is 3 a subset of 1, 2. So we can't tell whether either set is higher or lower on our hierarchy in any sense. They're completely unrelated to each other. However, if we can add one more restriction, that will let us accomplish this on certain sets. We say that a relation on a set is total if, given two elements x and y, x is related to y is related to x, or both. In other words, there has to be a relation of some sort between x and y in either order. We can't have two elements that are completely unrelated. If we add the restriction of totality to a partial order on a set, we will have what is called a total order on that set. For example, consider the less than or equal to relation on the integers. We can easily verify that this is a partial order on the integers. But as it turns out, it's also a total order. If an integer x is not less than or equal to y, then y must be less than or equal to x. 3 is not less than or equal to 2, for example, but 2 is less than or equal to 3. One more thing. Suppose we have a total order on a set. For every total order, we can create something called a strict total order on that set. We do this by taking out the reflexive property and instead making the relation irreflexive. When we create a strict total order on a set, given any two elements x and y, exactly one of three possibilities will be true. X is related to y is related to x, or x is equal to y. If a relation forces exactly one of these three possibilities to be true for any two elements, we call that relation trichotomous. Think about what this does to the less than or equal to relation on the integers. Since we've made the relation irreflexive, for the strict total order, we're simply left with the less than relation instead. So if x and y are integers, either x is less than y is less than x, or x and y are equal. Every possible x and y must satisfy exactly one of these three criteria. Well, that's enough about relations for this lecture. In the next lecture, we'll look at very special types of relations called functions and explore their properties. See you next time.